Hello everyone, I am Shashwat Srivastav from IIIT Hyderabad. I will be presenting work on FPGA Accelerator for stereo vision using semi-global matching through dependency relaxation. This work is jointly done with Ziol Chaudhary, Shashwat Khandelwal and Professor Suresh Purini. The outline for this presentation is as follows. We'll start with introduction. Stereo vision is a technique to construct depth map using two input images from slightly displaced cameras. This requires finding corresponding pixel from the left image for every pixel present in the right image. The distance between right image's pixel and its corresponding pixel in left image is called disparity, and from disparity we can construct depth map using the shown formula. Stereo matching algorithms are broadly classified into two types, local method and global method. In local method, we do block matching only along the horizontal scan line, whereas in global method, the objective is to find a disparity map D which minimizes the below objective function. The objective function comprises of two terms, eData and eSmooth. eData captures disparity map using local methods and eSmooth captures the smoothness constraint between neighborhood pixels. In our implementation, we have combined local and semi-global method to perform stereo matching. Algorithm consists of two steps. Step 1, apply census transform for local matching, and on top of it apply semi-global matching. So we will look at census transform first. We look for a matching block in the left image along the horizontal scan line for the highlighted block in the right image. The block is a collection of pixels. For example, we have taken 5x5 block, and this block's center pixel will be our processing pixel. So to find similarities between these two blocks, we first take census transform and then we apply Hamming distance. Census transform basically compares all the pixels of the block with the center pixel, and if the pixel is greater than the center pixel, we assign 1, otherwise we assign 0. When we get the two bit vectors, we take Hamming distance. Hamming distance is the number of bit positions in these sequences which are different. So similar the blocks, the lesser will be Hamming distance. So we move the block in left image by stride 1 to again calculate Hamming distance. We keep this going on till our maximum disparity. In our case, it was 64. So after constructing a 64 length vector, which we are calling as initial cost vector CT, we can report the disparity here only if we take the minimum and reports its index. So the map we generate, depth map we generate, it looks like this, which is quite inaccurate. To smoothen the output disparity map and increase the accuracy, we apply SGM on top of census transform. Next, we look at the semi-global matching. Semi-global matching method attempt to approximate the global methods by expressing the 2D smoothness constraint as an aggregation of multiple 1D constraints representing different directions. Specifically for hardware implementation, we can include only 5 paths which adhere to the scan line flow of pixels. So we divide these 5 directions into two groups. Group 1 is the horizontal direction group which consists of LR and RL. LR left to right, RL right to left. Other group, vertical direction group, which includes LD leading diagonal, TB top to bottom, and NLD non-leading diagonal. So the final updated equation after applying SGM we get is this. Here we have upgraded CT to a new vector called SP. This SP vector is the aggregate path cost vector. This path cost vector is an aggregation of all the updated path cost vector LR. Here R represents the directions which belongs to LR, LD, TB, NLD and RL. This LR update equation can be computed using shown equation. This equation basically depends on CT, the initial cost vector, and LR P minus R vector, which represents the path cost vector of pixel P minus 1 along the processing direction. So when we apply the SGM, we get an improved output. Hence, we have moved from this output to a much improved output. So next, before we move on to the hardware implementation, we look at the pixel dependencies. So suppose we were processing row I plus 1th pixel 7. So this pixel 7 depends on row ith pixel 6, LD pixel 7's TB, pixel 8's NLD path cost vector. And it also depends on pixel I plus 1th, pixel 6 for LR and pixel 8 for RL. So when we are processing pixel 7, this pixel will get all the vertical direction path cost vector from BRAM, and this BRAM was filled when we process row I. But when we process horizontal directions, there is an immediate dependency. Since pixel 7 can begin processing only after pixel 6 has given the output. So we propose a heterogeneous FPGA plus CPU stereo vision system. Left and right images are streamed from the host onto the line buffer. The line buffer is realized using block RAM. BRAM is parameterized, and in our case it is holding 7 rows. The BRAM then supplies two 7x7 windows to the CT module, which produces initial cost vectors. So first we look at the SGM LR module because this is special since it has immediate dependency. And due to that immediate dependency, there is a feedback. And at the same time, we are also storing these initial cost vector in a BRAM which has LIFO structure. So we refer each of these purple units as a processing unit, PU, and we can have n number of processing units depending on the resources available and FPS requirement. And since we are processing multiple pixels in parallel, we call this as pixel level parallelism. We have independent SGM units for all the directions. So for for vertical directions, we are getting LR from FIFO VRAM, and it's also storing its output in the FIFO VRAM for use in the next row's processing. The output of these 4 SGM units are then aggregated and stored in another VRAM which has LIFO structure for future referencing. So this begins the forward pass of first row. We are filling the VRAM. So as the forward pass finishes, SGM-RL comes into picture and it dequeues first row's last pixel's initial cost vector. And at the same time, line buffer is also getting data from the host. This helps us in maintaining a high compute to communication ratio. And as SGM gives us the updated path cost of RL direction, the cost aggregation unit adds all the previously aggregated 4 paths to the new RL path and gives us the output. Now SGM-RL is flushing first row, and at the same time second row's forward pass has begun. Then as first row is flushed out and its disparity is produced, second row's forward pass is completed. Now it will get flushed and third row's processing has begun. And in this similar fashion, we generate the whole disparity map. Now we look at the underlying architecture of CT module. CT module is parallelly pipelined across pixels. It takes in 2 windows. For example, we have taken 3x3 window. It does the census transform, generates the bit vector representation. Right images bit vector is stored in FIFO, left images bit vector is stored in a register of size 64x8. Here 64 represents the maximum disparity and 8 the bit vector length. Every time a new bit vector comes in, the register is right shifted first before appending the bit vector. And as we have all the 64 bit vectors of the left image in the register, then Hamming distance module comes into picture and it dequeues the first 8 bits from the FIFO and it takes the whole 64 length register to its input of Hamming distance. Hamming distance exploits disparity level parallelism and makes sure that it is producing initial cost vector in every clock cycle. Next we look at SGM underlying architecture. So SGM is a 3-stage pipeline which is implementing LR, the update equation. This uses tree structure to calculate minimum of LR P minus R, and it takes the input from BRAM since for vertical directions. For horizontal direction, we know that there exists an immediate dependency. And we also know that SGM module takes 3 clock cycles to produce output, and that output acts as input for the next pixel's processing. Therefore, this generates a stall of 3 clock cycles in the pipeline for processing every pixel. So to overcome this, we introduce a new thing called pixel dependency relaxation, which helps us in maintaining a steady throughput of producing updated path cost vector at every clock cycle. So we simply, without waiting for the output, we simply pass the available output to the input of the module. For example, while processing pixel 7, we would require pixel 6 LR, but we take pixel 3's LR because that was available. Therefore, this creates this pixel relaxation of 4. When we increase processing units to 2, the pixel relaxation further increases to 8 because we are receiving 2 pixels initial cost vector in a packet, and this packet is getting distributed amongst 2 SGM modules. First SGM module processes all the odd pixels and second processes all the even pixels. Due to this distribution, the pixel relaxation further increases to 8. We can see that for PU equals to 3, pixel relaxation is 12, and for P equals to 4, it is 16. In the next section, we'll see that this increase in pixel relaxation does not adversely affect the error in the disparity map, but the gain that we receive is proportional to the increase in PUs. We reported accuracy on Kitty 2012 and Kitty 2015 dataset. We calculate average error and percentage bad pixels for occluded and non-occluded pixels. The average increase in average error was 0.12 and increase in percentage bad pixel was 1.96% for every increase in PUs. So as for the frames per second kept increasing linearly when PUs were increased. So when we reached PU equals to 4, the FPS quadrupled with respect to initial PU, which was PU equals to 1. The increase in resources used in terms of kilolux also increased almost linearly. We propose a parallel pipeline Harvard accelerator for computing disparity map. We introduce a novel pixel-level data parallelism. Our hardware architecture proposes 1.6 times more FPS compared to the existing state-of-art SGM implementation of FPGAs. Our architecture is scalable and can be tailored according to the requirement of FPS, accuracy, and availability of resources. Thank you. This work was done in Computer Systems Group of IIIT Hyderabad.